Swayam Prabha. Digital India. Educated India.
Dear students, in the previous lecture we have studied the mesh analysis, in which we have identified the mesh and then applied the KVL in that mesh. So today we'll be talking about the another method for analyzing the circuit, which is nodal analysis. As the name suggests, we have to solve the circuit by using nodes. It means that in a given circuit we have to first identify the nodes, and then in that node one of the node will be taken as the reference. So generally the node connecting the greatest number of elements is taken as the reference node, and we assume that the reference node is having a potential of 0, okay, which is known as the ground node or the datum node or reference node, whatever we call. So with respect to that ground node, we'll be assigning the voltages at the remaining other nodes. So basically the total number of nodes will be n. Then leaving that one of the node as a ground node, we'll be applying the KCL in this nodal method at n minus 1 nodes. So we'll be taking an example while demonstrating the equations. So suppose you have two given nodes, node 1 and node 2. At node 1 the voltage is V1 with respect to some reference node, and the node 2 the value of voltage is 2 with respect to the same reference node. And node 1 and 2 is connected through a branch which is having some element Z, okay, and the current which is flowing through that is I. Now using the Ohm's law we can write that V1 minus V2 by Z is nothing but the current. So this is the way we'll be writing the unknown current in the branch which is flowing between the two nodes. So this is just a demonstration of the assumption of the branch current. So in the nodal analysis we'll be assigning some voltage to the node circuit. So now let us consider some circuit. So let me draw one small circuit or the network which will be solving for a solution using the nodal analysis. So in this particular circuit, the most number of elements are connected at this bottom line. So we can take this as a reference, okay, the n. So n is basically the reference node, and the voltage at node n is nothing but 0. So with respect to this reference node or the ground node, we are assuming the node 1 and node 2, and the node 1 the voltage is V1 and V2. So we'll write here as 1 and here as 2. This is node 1 and this is node 2, okay. So node 1 the voltage is V1 with respect to the reference node, node 2 the voltage is V2 with respect to the reference node. Now from this direction one current is coming which is IS1. Let us give them as a value as this, and this side the current is IS2, okay. This is the direction of the current and this is the direction of current. So I assume some direction of the current. This is suppose I1, this current is I2, so from here I2 is coming anyway, so it is I3, and this is anyway IS2. So from this circuit, if you try to find out the value of I1, okay, We can write this as small, so let us not go into the detail of representation. So here I1 will be V1 minus 0, the reference node, by R1, which is nothing but V1 by R1, and 1 by R1 is nothing but the conductance, right? So this is G1 into V1. Okay. Similarly, what is I2? I2 is nothing but V1 minus V2 by R2, which is nothing but G2 V1 minus V2. Then what is I3? I3 is the voltage across the element R3. So V2 minus 0, the reference node, by R3. So if you can write it as a G3 into V2, or simply G3 V2. Okay. What we'll do, we'll apply the KCL. So apply KCL at node 1. What we'll get? So total incoming current equal to the outgoing current. So incoming current is IS1 and outgoing current is I1 plus I2. So we can write IS1 as, substitute the value of I1 I2 from this equation, G1 V1 plus G2 V1 minus V2. So basically this will be, or we can rewrite this equation as G1 plus G2 times of V1 minus G2 V2 is equal to IS1. Okay, so this is the equation number A. Now similarly, apply KCL at node 2. When you apply the KCL at node 2, we can write the equation. You can have a look here. So from here you can write it as I2 plus I3. Isn't it? So total incoming current is I2 plus IS2 and leaving current is I3. Now substitute the values. So we can write it as V1 minus V2 times of G2 plus IS2 is nothing but G3 V2. Okay. So just arranging the terms, we can write it as minus G2 V1 plus G2 plus G3 times of V2 is nothing but IS2. This is equation number B. So as you can see, in case of a mesh analysis, we have written the equation in the matrix form, which was easy to solve the circuit. Now similarly here also we can write the equations in the form of the matrix. So from A and B, if we write the equation in terms of matrix, we can write unknown variables as V1 and V2 for the two nodes, and then we can write equation as IS1, IS2, and this is G matrix, G1 plus G2 minus G2 minus G2, G2 plus G3. Okay. So basically this is a G matrix and this is V matrix and this is I. The order of this will be n by n. This is n by 1. This is n by 1. Where, one second, where n is the number of nodes. Leaving the reference node. Okay, so n is the number of nodes leaving the reference node, because these voltages are calculated with respect to the reference node, which is known as 0. So other voltages are not known, but the voltage at the reference node is already assumed as 0. So n is the number of nodes, that is a leaving reference node. Okay, so this is the conductance matrix. This is voltage at the given node or the node in the circuit, and then net current. Okay, so here in this particular representation, these IS1 and IS2 are the node currents. Okay, so basically at a given node, if there are different current sources which are connected to that node, the total sum of all the currents will be taken as IS1, basically the source currents, which will appear in the right side vector in this matrix representation. So generally the current entering at the node is taken as positive. So we'll be taking an assumption that the current which is coming to the node is positive and leaving the node is negative. So this is the assumption we'll be taking. Okay. So this is the complete process of applying the nodal analysis. So let us recall. The first step is to find out the total number of nodes. So let us consider an example, then we'll see what are the requirement of the nodal analysis. So for example, we'll consider one small circuit. Okay. So in this particular circuit, how many nodes you can see? Okay, let us tell me the total number of nodes. Okay, so suppose this is IS1, this is IS2, R1, R2, R3, R4. Okay, so this is the given circuit. So identify the number of nodes. So we can assume that this is as a reference node, and then we have one node here, one node here, and one node this one. So we can just mark them. Node 1, voltage is V1, node 2, voltage is V2, node 3, voltage is V3. Fine. Just encircle that so that we do not get confused. So these are the three nodes which are identified in the circuit. So the current which coming to this branch is known. So let us assume this current as I1, this current as I2, and then this current as I4 through R4, and the current this is I3. So basically what is happening, one current is coming from here is I3. So this is the complete assumption of the node voltage and the current which is flowing. Okay, so in this particular circuit, the step 1 was the identification of the number of nodes, and one of the node will be taken as a reference. So we have taken this node N as a reference node. The voltage at the reference node is 0, and the remaining nodes 1, 2 and 3 are assumed as one voltage V1, V2 and V3. Then we have assigned the currents. Now consider this as R1 as 1 ohm, R2 as 2 ohm, R3 as 3 ohm, and this is as 4 ohm. And the value of IS1 is 3 ampere, IS2 is 2 ampere, for example. Okay, now these are the values given. Okay, so for solving the circuit, we can, one of the method is like, okay, we apply the directly the KCL at all the nodes. So we'll do it conventionally by applying the KCL. So apply KCL at node 1. When we apply the KCL at node 1, we can write it as the total incoming current is IS1 plus I3, which is nothing but the I1. Okay, so we can write the equations. This is 3 plus I3 is nothing but V3 minus V1 by R3, which is 3 ohm. I1 is nothing but V1 minus V2 by 1. So if you solve this and collect the terms, we can get it as a 4V1 minus 3V2 minus V3 is equal to 9. So this is equation number 1. Okay, now apply KCL at node 2. So look at the node 2. So the total incoming current is I1 plus IS2, which is nothing but I2. So in this, substitute the values. Okay, after substituting values, I1 is nothing but V1 minus V2 by 1 plus IS2 is 2 ampere, or we can just write the numerical value. So IS2 is 2, which is equal to I2, which is V2 by 2. So when you just solve the equation and collect the terms, it will be minus 2V1 plus 3V2 is equal to 4. Equation number 2. Now KCL at node 3. When we apply the KCL at node 3, it will be, look at the circuit, the total incoming current is nothing, so 0, and the outgoing current is I3, I4 and IS2. So is nothing but IS2 plus I3 plus I4 is equal to 0. So this is basically 2 plus V2 by 3, V3 by 3 V3 by 4 ohm plus I3 is nothing but V3 minus V1 by 3 is equal to 0. So now if we just collect the terms, minus 4V1 plus 7V3 plus 7V3 is equal to 24 with a negative term. So this is equation number 3. Now we have 3 unknowns, V1, V2, V3, and 3 equations as 1, 2, 3. So we can solve it for V1, V2 and V3. But we can do it by alternative method. What is that alternative method? Which is directly writing the equations in the matrix form. Okay. So directly writing the equation in the matrix form. So this is the circuit or network having node 3. So the order of the conductance or the node conductance matrix will be 3 by 3, and this will be 3 by 1, and the source current at different nodes can be at 3:1. So this is V1, V2 and V3. This is G11, G12, G13, G21, G22, G23, G31, G32, G33, and this is nothing but I1, I2, I3. So in this particular representation, is there a possibility to write this matrix as we wrote mesh impedance matrix? So what is G11? G11 is basically sum of all the conductances of all branches which is connected to that particular node. So G11 is basically sum of all the branch conductance connected to the node 1. Okay, similarly G22 will be the sum of all the branches. We can just write G22 is nothing but sum of all the conductance connected to node 2, and G33 is sum of all the conductance connected to the node 3. So this is the diagonal term like G11, G12, sorry G22 and G33. Okay, now what is G12? G12 and G21 are nothing but the negative sum of mutual conductance. Mutual conductance means which is between node 1 and 2. Similarly, G23 will be G32 is also the sum of mutual conductance between node 2 and 3. Okay. Similarly, G12, 21, 23, 31, 13, which is G31, which is nothing but negative sum of between 1 and 3. So this is all the conductance which is mutually shared is the non-diagonal terms, and the self or the total number of conductance which is connecting to the number, I mean the sum of all the nodes which are connected will be taken as the diagonal term to the specific node. So now using this we can mark it as A. So can we write the equations in our case? So what is G11? Try to find out the term G11. So at the node 1, if you see the total conductance is nothing but G1 plus G2. This is a sum of total conductance which is connected to node 1. G1 plus G3. So this is nothing but 1 by 1 plus 1 by 3. 4 by 3. Similarly, what is G22? G22 is G1 plus G2, which is nothing but 1 by 1 plus 1 by 2. And this is mho, not ohm, because this is conductance. So this is 3 by 2 mho. Similarly, what is G33? G33 is G3 plus G4, which is 1 by 3 plus 1 by 4. 7 by 12. Okay. Now G12 or G21, it is nothing but negative of G1. Okay. Negative of G1. So which is nothing but 1 by 1 minus 1. Or you can represent it by Siemens S. Mho or Siemens is the same unit for conductance. G23 or G32, which is nothing but sum of conductance which is common to branch 2 and 3. So if you go to the circuit between node 2 and node 3, there is a current source, but there is no conductance between these two nodes, so the term will be 0. Now G13 and G31, which is nothing but negative sum of node between 1 and 3. So between node 1 and node 3 there is an element R3. Okay, so it is G3 minus G3, so minus 1 by 3 Siemens or mho. So from here we can clearly write a nodal conductance matrix. So that is nothing but 4 by 3. Then another R1 2 is minus 1. Then 1 3 is minus 1 by 3. 2 1 is minus 1. 2 2 is 3 by 2. And 2 3 is 0. Then 1 3 is minus 1 by 3. This is 0 and this is 7 by 12. Okay, into V1, V2, V3. Now what is this? The source current, right? So what is the source current which will be taking? Is nothing but what is the source current which is at node 1, which is IS1, which is 3 ampere. At node 2 the incoming current is 2 ampere. At node 3 the source current is leaving at 2. So this term we'll see, the source which is connected to 2. So in our assumption we have taken the node current which is coming as positive, right? So at node 1 the source current is IS1, it is coming to the node positive. Node 2 IS2 is coming to the node positive, and 3 node which is coming to the node 2 is positive, and at node 3 the source current IS2 is leaving, so it is minus 2. So IS2 is minus 2 ampere for node 3. So this is why it is reflected here at minus 2. So this is nothing but G V is equal to I. So we can directly write this matrix and solve the circuit. So this is all about the node analysis. So there is something, some case where we can find that all the voltage source which is connected should be converted to the current source. But when a battery is connected between the two nodes, how can we take that circuit? Let us see the difference when we apply the nodal analysis for AC circuit. So nodal analysis for AC circuits. Okay, so we have talked about the resistive circuit and found out that the matrix can be written in the form of a conductance and then multiplied by the voltage, we get the current. So in case of DC circuits, we have a matrix representation of G into V is nothing but the source current I. Okay, now in case of AC circuits, we convert it into the following form: Y into I, where Y is nothing but the admittance matrix, node admittance matrix, and this is nothing but 1 by Z. So Y elements are complex numbers, whereas in G those were the decimals or regular non-complex quantities, correct? So here these are basically the complex quantities. Okay, so basically the real plus j times of imaginary, this kind of numbers will be there. Similarly, the voltage here will be in phasor quantities, the current will be a phasor quantity. So here the voltage and current will be phasor quantity. So this is the difference. The process will be the same, but the quantities will be the complex and the phasor. So let us consider the example. So the given circuit is, suppose and you have a voltage source. This is 60 angle 0. This is 6 ohm. Suppose there is a inductor whose value is J4, capacitance minus J5. Here it is assumed as 8. Here you can think of as 4. And this AC voltage you can consider as 80 with some angle, suppose 30 degree. So this is the given circuit. So in this particular circuit, when we try to apply the nodal analysis, you have to figure out the number of nodes. So let us find out the number of nodes. So this is considered as a reference. So this is the one node, node 1, node 2, node 3, and this node as a fourth node. Okay. So in this circuit, you can clearly see that the total number of nodes are 5. Total number of nodes are 5. But the nodal equation will be applicable to 4 nodes, leaving the reference node, because we know the voltage at the reference node is 0, which is known. So remaining V1, V2, V3, V4. So we have remaining unknowns V1, which is on node voltage V1, V2, V3, V4. So V1, V2, V3 and V4 are unknowns. We have to solve this equation, which is having 4 variables. So the set of 4 equations. Now similarly, we can just choose wisely and look at the circuit very carefully. And what we can do, we can convert the voltage source into current source. Okay. So when you convert this, you can clearly see this voltage source and this voltage source, both sides, they are in series with some element, here in this case resistance, but even it is not resistance, you can convert this by similar manner when it is replaced by some impedance, like if it is inductance or combination of RL and C, that conversion of the source can still be done, but the R will be replaced by the Z. So now if we draw the same circuit by converting this into the current source, so we can see that we'll be having a current source, then parallel element, then we have a inductor, then we have a resistor, then we have here as a capacitor, similar circuit. Here we get a change and here it will be a current source. So this is the new circuit after the voltage source is transformed into the current source. Now look at the circuit and see how many nodes are there. So by that time I'll just write the values, so you can figure it out how many nodes you can see in the circuit. this is 4 ohm. So this will be nothing but voltage by 4, which is 20 angle 30. Okay, so this current source is this. So now you can clearly see that total number of nodes are only 3, and the unknowns are node 1 V1, node 2 V2. So unknown voltages are V1 and V2. Here you see, and here you see. You can clearly see the difference. Now that this system will be very easy to solve. If we get to know the V1 and V2, we can get to know all the currents in every branch which is flowing through it. So now let us write the equations. So what we can do, we can just write the equations in this form. Okay, so what is the nodal admittance matrix? So at node 1, and suppose this is this form. So this is the voltage V1 and the V2. The total source current at V1. So we have assumed that the current which is approaching is to be taken as positive. So this is 10 angle 0, and the V2 will be 20 angle 30. This is also approaching the node, so it is taken as positive. Now this is the total admittance connected to node 1. So this can be 1 by, this is nothing but we can just look at the circuit. It is 6 ohm, correct? This is 6 ohm. Now we can write this. This we can write as 1 by 6 plus 1 by J4 plus 1 by 8. This is the total admittance, this branch, and this. Okay, these three branches are connected. And the common branch between node 2 and 1 is 1 by 8, negative of the admittance. Similarly, 2 and 1 and 1 and 2 will be same. Now the node 2 is having 1 by 8 plus 1 by minus j of 5 plus 1 by 4. Okay, so these are the total admittance connected between the two nodes and the nodal matrix. So this is nodal admittance matrix. This is unknown, and this is the source current which is pointing towards the node. Otherwise it will be taken as negative. So in this circuit, if you want to solve, you can clearly write down del as the determinant of this following quantity. Then 1 by 8 plus 1 by negative of j5 plus 1 by 4. Okay, and when you solve it, you can find this value as 0.148 angle of minus 13.8. Okay, so this is the magnitude of this del, which is a nodal admittance matrix. Now del 1 is nothing but, you can assume is 10 angle 0 and 20 angle 30. This is 1 by 8, right, and then 1 by 8 plus 1 by minus j5 plus 1 by 4. And if we solve it, this is going to be 6.748 angle of 28.78. Similarly, del 2, go a little up, this is nothing but 1 by 6 plus 1 by j4 plus 1 by 8, negative 1 by 8, 10 angle 0, 20 angle 30 degree. And if you solve this, you'll get 8.911 angle of negative 9. Okay, from here the V1 will be nothing but del by del 1. Okay, so del 1 by del, put the values, get 6.748, angle of 28.78 divided by 0.148, angle of minus 13.8 degrees. We'll get the answer as 45.59 and angle of 42.58. Similarly, V2 will be nothing but del 2 by del, which is 8.911, angle of minus 9.1 degree divided by 0.148, angle of minus 13.8 degree. And if you solve this, the answer it comes as 60.2, angle as 4.7. Okay, so this is the answer for the solution. Now we know the V1 and V2, so we can know all the current using Ohm's law. The current which is going here, 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 current anyway is coming here. So we know all the current in different branches, and then this is how we are going to apply the nodal analysis in AC circuits.